with the equation solving stuff under our belt, we can actually talk about applications of logarithms and exponentials, logarithmic functions and exponential functions. So we've got a couple of examples here to kind of illustrate some of those sorts of things and mention some of the ways that we can model certain behavior with the exponential functions. Really, that's mostly what we're talking about. I'll comment on the logarithm stuff in just a moment. How we're bringing in the equation solving stuff. As far as the logarithms are concerned, because of the way that those show up, if you have an application where a logarithm is used, they'll actually tell you what that model looks like. So they won't expect you to know some sort of basic format. For instance, here with this first example, compound interest, something that we might be aware of from having a bank account, like a savings account or money market account, from having a certificate of deposit, from having a retirement account, something we might be aware of instead because we have a home loan, a mortgage, something we might be aware of because we have a credit card. The compound interest, the standard compound interest, is the kind of interest that would apply to those different situations. So we have this set structure for how standard compound interest is supposed to work. We don't really have that kind of thing with these different situations that have logarithms. We're not expecting you to remember those structures. Those would be given to you as part of an exercise. We would still use our equation solving skills, as we'll see in the examples here in this video, but they're not going to expect you to remember, here's how this logarithmic model is supposed to be set up. They do expect you to know what everything means when we talk about the standard compound interest or the idealized version of things, which we talk about as the continuously compounded interest. Come back around to that as well in a moment. The first example that we've got is a standard compound interest, because when we find mention of how that interest is compounded, it doesn't say continuously. That's the key thing. Continuously versus anything else. Anything else than compounded continuously means that we use that standard compound interest formula. And that standard compound interest formula has these different letters that are mentioned. A for the accumulated amount, P for the principal, the original amount, R for the interest rate, used as a decimal, time, T, and the N, that's the number of times that we get the interest. So we start out with stuff that we do clearly pick up on with this example. We have a $10,000 investment. We're starting with $10,000. Boom, stack of cash. I want to make an investment. There's my money. So that's the principal. 4%. Okay, that's our interest rate, but we got to kick that over into a decimal. So decimal 0.04. Over a 12-year period, okay, cool, T is 12. So if they're asking us to find the amount, we're going to look for the A. That means that we're still missing this N number that would go into this formula. How many times every year does interest get applied to our account? Well, they tell us daily. How many days are in 1 year? 365. So the number of times per year that we get interest, N, is 365. We can put those numbers into our formula, and this is just, as we call it in the math biz, plug and chug. Plug those numbers into your formula, plug that entire calculation into your calculator. One of the things that I want to mention while we're here is that when you plug something like this into your calculator, make sure that you use parentheses around that 365 times 12. That way you're correctly telling your calculator what that power needs to be. So if we're using a modern scientific calculator, especially a graphing calculator, we can type in the 10,000, parentheses, 1 plus 0.04 slash 365, close parentheses. Then we need to tell it that we have a power, so we hit our power button, and then we don't just type in the 365 times 12. Calculator would only use the 365 as the power. Oops, that would be bad news bears. So we tell the calculator, after we hit that power button, parentheses, 365 times 12, close the parentheses out, hit enter, get that final amount, $16,160.32. What? They didn't say anything about rounding. We know what's going on with money. We know that money is dollars and cents. They don't need to tell us anything about rounding a money value that's showing up at the end, because we should know from our real world experience. And that's something else that comes to bear with some of these other examples. For instance, we can talk about exponential growth, and the commonplace joke is about bunnies multiplying everywhere. If we're talking about bunnies, we're going to start out with a whole number of bunnies. If we're talking about bunnies, we're going to end up with a whole number of bunnies. I don't know about you, but I don't want to come across 0.4 of a bunny in a dark alley someday. No thanks. There are going to be these real world sorts of situations where we might not have to be told the rounding. We're going to just need to understand what rounding we should do based on the actual situation that is mentioned in the exercise. So for money, dollars and cents, unless they tell you something different, like round to the nearest dollar. Okay, cool. Thanks for specifying that, because I normally wouldn't do that. I would normally round to the nearest penny. If they don't tell me anything, I'm going to round to the nearest penny, because that's just the way that money works. If we're talking about growth and we're talking about bacteria or bunnies, we're going to round to whole numbers if we're calculating a final amount or an original amount. Exponential decay. Hey, look at that. They look the same. The only difference is what's happening with decay. We usually would say that decay is tied to the growth rate or the decay rate. There's another way to do this that you may also end up discussing depending on your textbook or depending on where your exercises are pulled from. So there might be another set of models for your exponential growth and your exponential decay. They will look a great deal alike as well, but different sort of setup depending on how you are bringing into play that growth rate. So this is just merely one of those ways that ties back in with the idea of the compound interest. The business with the compound interest, by the way, and the continuously compounded interest, if we go from daily down to hourly, if we go from hourly down to every minute, if we go from every minute to every second, we're increasing that number that we have for the n. And the way that all of that stuff ends up working together is if that number keeps getting bigger and bigger and bigger and bigger, and it keeps getting to be that your interest is applied more and more often, the idealized situation is that interest is compounded continuously. Not just every second, not just every 10th of a second even, not just every 100th of a second even, continuously compounded interest. So the idealized version turns this formula that we see into one of these that has that natural base, E, showing up. Being a chemistry fan, I like to have in an example of the radioactive decay. One of the aspects of radioactive decay is that rather than giving a rate like a percent, it's a lot more convenient to talk about what's called half-life. So this is an amount of time that refers to how long would it take for an amount of some sort of substance to get cut in half. We could get a continuously compounded interest example and then throw in the chemistry example. Because apparently I forgot that there was that continuously compounded interest example. Whoops. So as far as that continuously compounded interest example, compounded continuously. That's the thing that I'm looking for, that is that deciding aspect of which interest formula do I use? Do I use the standard compound interest formula or the continuously compounded interest formula? So we've got far fewer values to worry about in that particular formula. When we start looking at what's in that formula, we have our principal, our time, our rate, and our accumulated amount. But in this particular situation, it seems when we're looking for numbers, the only number that they tell us is 3.9%. So cool, 0.039, and they're asking nearest year, so apparently we have to figure out the time, but what about the principal and what about that accumulated amount? Well, they've got to give you enough. They might give you more, but they definitely guaranteed must give you enough information for you to be able to put things together, set up your equation, and be able to reasonably solve it. So there's got to be something else in the statement of this exercise that connects together the principal and that accumulated amount, and it's double an investment. If I start with $1 and I want to double it, boom, got two. If I start with $10,000 and I double it, I end up with $20,000. Double the principal. Well, I don't know what the principal is. They didn't tell me, so I can just use a generic version, 2p. 2p as my accumulated amount equals my principal. I don't know what it is, but I don't care because it turns out it's not going to matter. Put my interest rate in there as the 0.039 times t. We've got to solve for t, so we got to use those equation solving skills. We got to get that exponential chunk by itself, divide on both sides by p, and look what happens. No more p showing up in that equation. So the deal is with any time that we might double something, triple something, quadruple something, cut something in half instead, doesn't matter what we start with. That's going to actually end up finding its way out of the equation that we've got to worry about. So 2 equals, well, I got that exponential. I'm going to rewrite that exponential in logarithm form. So logs are equal to powers. The only thing that's left is the 2, so the 2 has to go inside of that logarithm. And then, hey, I get the t by itself. I just got to divide by the 0.039. And if I'm rounding to the nearest year, that's going to calculate out to 18 years. Having forgotten about that one, instead I was thinking of this example. The half-life of carbon-14 is 5,730 years. Again, what does that mean? That means you start out with a lump of carbon-14. It's going to take 5,730 years for that lump to become half of its original size. How much of a 30.0 gram sample to the nearest tenth will remain after 2,101 years? Okay, we know the half-life, but when we talk about that formula, we don't know what this K number is. other than because this being a decay issue, we know k is a negative number, we don't have the k number itself. We have to bring in that half-life business. I don't know what the original amount is, but I know that the ending amount is half of what I started with. Half of that original amount, which again means we know, I've told you, you can take it as a certainty. We know that that original amount is not important. We're going to see that that ends up disappearing from the equation. We've got our time. We don't have the k. So when we start rearranging things, getting that exponential by itself, that original amount divides out, no longer appearing. Rewrite as a logarithm, divide. We're going to take this calculation, we're going to run it through our calculator, and then we're going to store it. Because we don't want to chop that down to a fewer number of decimal places. We want to keep that entire figure. So the nicest thing for us to do is store that in the calculator so that we can use it in the other part. And that's the part where they literally are asking how much is left, starting with the 30.0 grams after 2,101 years have passed. The k value is stored in the calculator. The t is the 2,101 years. The original amount is the 30.0. We've got enough information to find that final amount. And we're going to again run that in the calculator. We've got that value stored. We're going to make sure that we're careful about that exponent business, putting parentheses around the stored k value times the 2,101, getting us approximately 23.3 grams as that final amount.